Describing circular motion. At the end of this lesson, you'll be able to describe the motion of an object traveling in a circular path. A lot of vocabulary with this lesson, so make sure you get it all down. It's going to help with understanding all of the other information loaded throughout this lesson, and there is a ton. Centripetal, first of all, means center seeking. Angular acceleration is the rate of change of angular velocity. The symbol is alpha, not A, alpha, and the unit is rad per second squared. More on that later. Angular displacement is the number of radians you have traveled through. The symbol is theta, and the unit is rad. Angular velocity is the circles completed per second, and the symbol is omega. The unit is rad per second. A lot of Greek letters here too. Centripetal acceleration is the net acceleration directed toward the center of the circle, because centripetal means center seeking. Circumference is the distance around the circle. You remember the circumference formula as 2 pi r. Period is the amount of time it takes or would take to complete a circle. The symbol is capital T, and the unit is seconds. Frequency is the number of cycles or occurrences per second. The symbol is F, lowercase f, and the unit is 1 over seconds, or a hertz. It's the inverse of your period. Hertz, the unit of frequency equivalent to 1 cycle per second. Inertia is the resistance of an object to change its state of motion of path. More mass, more inertia. Translational motion is linear movement along an axis. Radians are a unit of angular measure related to the radius of a circle. Rotational motion is motion about an axis. And when I say about an axis, I mean around an axis. Uniform circular motion is motion around a circular path with a constant speed. Period is the time it takes for objects, or the time it takes for an object to potentially complete one cycle. Frequency is how often the cycle is completed. Earth's period about its own axis is 24 hours or 86,400 seconds. Earth's frequency about its axis is 1 over that, or 0.04 cycles per second, or 0.04 hertz. Earth's period around the sun is 365.2418 days. The moon's period about the Earth is 27.3 Earth days, while its period about its own axis is the same. That's why the moon appears to be facing Earth in the same way every time you look at it. Frequency is 1 over the period, and period is 1 over the frequency. Period and frequency are inverses of each other. Here's some just testing yourself. Check yourself. Pause the video in between each of these to see if you know whether or not it's a period, frequency, or other. Second hand of a clock takes 60 seconds to travel around the clock. Period, the time it takes for one complete cycle. The hour hand of a clock traveling around the clock twice a day is frequency. Each second as it orbits the Earth travels 18 miles. Frequency. The Earth rotates 30 times every month. Frequency. The Earth takes 365 days to complete one full orbit around the sun. Period. A trucker averages 600 miles every day. That's other. That is a linear distance. Gotcha. Degrees versus radians. A degree is just some way to divide a circle into equal pieces. In fact, we could use any other means of division, including arc minutes, which is 21,600 divisions or 60 divisions per degree. Or arc seconds, which is 1,296,000 divisions or 3,600 divisions per degree. We don't want to deal with that. Instead, we're going to rely on the radians. The radians are reliant on the geometry of the circle, the radius of the circle. The purple line here represents the radius. If I peel up that radius and I slide it along the circumference of the circle, that distance that I've covered is 1 radian. Guess how many times I can do this before I make a complete circle? 2 pi. the circumference equals 2 pi times r. A radian is just the equal division of the arc length based on the radius of the circle. We call this unit rad even though it's really just a placeholder. It's completely dimensionless. More on that coming up. Move myself out of the way here. A radian is that. Oh, conversion factor. Remember, 1 degree equals pi over 180. Some more geometry review here. Remember the arc length formula from your SAT prep or geometry class. We're going to be using it, only slightly changed. For us, I like to use this formula rearranged for theta, and instead of using S, I like to use X. I like to think about this equation as our translational or linear displacement put over a circle. So it looks like that. So our linear displacement over a circle or over the radius gives us our angular displacement. The image shows you the angular displacement. X is the linear distance or displacement measured in meters. Theta is the angular displacement measured in rads, and r is the radius measured in meters. When I look at the units for this formula, I see that x over r, each of those are measured in meters. So the units completely cancel out. So to remind ourselves that we're dealing with rads or radians, we're going to use the unit placeholder, rads. But it's completely dimensionless, that's just there. Just like we took the linear quantity and put it over radius, we can do the same thing with velocity. We can take our linear velocity and put it over radius, and we're going to get a new Greek letter omega, which is our angular velocity, or circles per second. Here, omega is the angular velocity measured in rad per second. V is the translational or linear velocity measured in meters per second. And r is the radius. When we look at the units, remember that rad is just a placeholder to remind us we're looking at circular motion because those meters cancel out. Guess what? We've also got translational acceleration, so we also have an angular acceleration. We're going to complete the same pattern. We're going to take our translational quantity a and put it over r, where alpha is the angular acceleration measured in rads per second squared, a is the translational or linear acceleration measured in meters per second squared, and r is the radius measured in meters. Again, those meters are going to cancel out. So another thing to think about when we're talking about angular velocity, we have our average velocity equation, which tells us our displacement over time gives us our average velocity. We can do this same thing with our angular quantities. So we can say our angular displacement over time is equal to our angular velocity. The relationships are all still there. If you are using calculus, d theta dt, same thing as dx dt. We can also do d omega dt for our angular acceleration. All of that stuff is still the same. It's just now we're dealing with angular quantities, and the units are slightly different. All right, look at this picture. We've got two different radii moving with the same angular speed. They're completing the same number of circles per second. But which one's traveling more or traveling farther? It'd be the blue one. And because it's completing that farther distance in equal amount of time, we would say the linear velocity of the blue one is greater. The distance that the blue one is traveling is 2 pi r divided by time. That'll give us our linear velocity. Because the blue circle has a greater radius than the red circle, the blue circle has a greater translational velocity. Gears work when multiple gears move at the same tangential velocity. Smaller gears are going to go through more angles per second, like you see here. And the bigger gear goes through less circles per second. So smaller angular velocity for the larger gear. These gears are connected with a chain but you can also have gears connected with interlocking teeth. They, of course, have to have the same angular velocity. These gears on a bike are going to allow you to either pedal easier or more difficult, more pedals, based on the terrain or the situation that you're going through. If you've got a mountain bike, you have multiple gears on the back wheel, and those gears have different sizes. So you get this different front gear to back gear ratio. A smaller front gear is going to decrease your speed by covering less angular displacement with each pedal rotation. That's going to reduce your angular velocity, which is good for climbing steep hills or keeping control of your bike. Meanwhile, if you're in a bigger gear, bigger wheel gear, which is a lower number, these are going to increase your angular displacement with each pedal. So your angular velocity will go up. This is useful for flat or downhill terrain. Let's look at these spheres traveling in a circle. Because a blue sphere is traveling a farther distance in the same amount of time, the distance it's traveling is 2 pi r, the tangential velocity of the blue sphere is greater. Meanwhile, the angular velocity is the same for both the blue and the red. Tangential velocity is the velocity vector that is tangent to the circle at any given instant. You can see the tangent velocity vectors attached to these spheres. Hopefully, you can also see the magnitude of these vectors is not changing. So we could say the spheres are moving at a constant speed. They can't be moving with a constant velocity because velocity has magnitude and direction, and the direction is definitely changing. If the magnitude is not changing, but the direction is, that must mean there's some acceleration. Onto the bridge equations. There they are. Following the same pattern, Greek letter equals linear quantity over radius. These three equations allow us to use linear quantities to see how the translational and rotational quantities are related. I call these the bridge equations because they bridge our translational equations to our rotational equations. It's important because, just like we had translational kinematics with constant acceleration, we'll also have rotational kinematics with constant angular acceleration. So there's our translational land equations as we know them. Then we have a bridge to get over there. These three equations bridge the gap, or bridge the dimensions from translational to rotational. And then finally, we have our rotational equations. These are going to look really scary. Don't let them scare you, because they are the same exact equations. All I've done is wherever there's a v, I've substituted omega. Wherever there's an x, I've substituted theta. Wherever there's an a, I've substituted alpha. They work exactly the same. They're not new equations. They're just a different look to the equations. Similar to when we had the x equations and the y equations when we were dealing with projectile motion. Uniform circular motion conditions. Here we have a green sphere going around a circle. You'll notice the tangent velocity vector is red. The acceleration vector is pointing towards the center of the circle. And our angular velocity shows that we're moving counterclockwise or anti-clockwise. The speed is constant for this object, and the speed is tangent to the circle. Again, acceleration directed towards the middle, and the magnitude of that acceleration is constant. Also, our radius is constant. Centripetal acceleration will point towards the center. And centripetal acceleration is the net acceleration that points towards the center. Centripetal means center seeking. So whenever you're talking about centripetal acceleration, that's acceleration pointing towards the center. Centripetal force, that's coming up. Here's our centripetal acceleration formula. It's v squared over r. That v is your tangential speed over r. We can substitute in the v over r relationship for omega, and we get omega squared times r. Either one of these will work for you depending on the situation that you're in and the givens that you have. Well, if you remember that force and acceleration are directly proportional to each other, and you're worried about Newton's second law, there's no need to fear. It still exists and is intact. However, we're moving around a circle, or whenever we're moving around a circle or on a circular path with a constant speed and a constant radius, we are in what's called uniform circular motion. We do not need to travel in a complete circle to be in uniform circular motion, though. When we are studying an object traveling in uniform circular motion, however brief that may be, our net force will get a new name. Guess what it is? If the net force is directed towards the center, it is center-seeking, then we have a centripetal force. And the centripetal force is going to be just the name of the net force that's directed towards the center of the circle. That makes it go in minus the stuff that makes it go out equals mass times our centripetal acceleration. The in forces minus the out forces equals mass times acceleration. Because centripetal force is just a name for the net force directed towards the center of a circle, a free body diagram will never have a force labeled centripetal force. Again, centripetal force is just a name for the net force directed towards the center of the circle, and a free body diagram will never have a force labeled centripetal force. For emphasis, centripetal force is just a name of the net force directed towards the center of the circle. A free body diagram will never have a force labeled centripetal force. Now that's not to say there's not going to be a centripetal force, because a force is a force, of course. And a centripetal force could be anything if there's only one force acting. Something I like to remind students here is that F equals F. Force equals a force. So whatever force you have could be substituted wherever there's an F or wherever there's an MA. Don't forget that. So that means a string may be the one force directed inwards, so the tension here is the net force. So tension is the centripetal force. So we can set our tension force equal to mass times centripetal acceleration, because tension is the centripetal force. Because the net force is only given by the tension force. If you remove the tension force, then you no longer have a centripetal force. So if we cut a string with an object going around, then the object's just going to continue along the tangent velocity path at that instant. Let's say we've got friction force as being the only force for an object going around a circle, and we wanted to find the coefficient of static friction. And stuff that makes it go, or stuff that's directed inwards towards the center of the circle, minus the stuff that holds it back, or the stuff that's pointed out of the circle, in this case there's nothing, equals mass times our centripetal acceleration. And then we can substitute in our frictional force equation to get mu equals mg equals m times ac. Remember that ac equals v squared over r, so we can make that substitution as well and solve for whatever it is we need. Still the same stuff that we've been doing, just now we have this extra label. Let's say we have a force at an angle in this case. Now our centripetal acceleration is directed towards the center of the circle. This is a special type of situation called the conical pendulum. We're going to look more into this, of course, with practice. But just because we don't have a force that's directed inwards towards the center of the circle does not mean there's not a centripetal force. There has to be a centripetal force for an object to undergo uniform circular motion, even if it's just a piece of that force. So in this case, it's the horizontal component, Ft sine theta. Or it could be any other force, as long as there's a force or component of force that's pointed towards the center of the circle. A word about roller coasters. In real life, engineers use a stretched out circle called a clothoid loop, as seen on the right, rather than a perfect circle, to allow for increased comfort where you don't have steady forces, but instead have changing forces acting on you. In physics, we typically simplify these loops to be circles unless otherwise stated. But here we see the bottom of a circular loop. We have the normal force is greater than gravity. The net force is still directed towards the center of the circle. Stuff that makes it go in minus the stuff that makes it go out equals our net force, mass times centripetal acceleration. We feel whatever the normal force is. If the normal force is greater than gravity, we feel heavier. If the normal force is less than gravity, we feel lighter.